All right, sequences and series. So we got a couple of mystery series here. We're going to try and figure out if they converge or diverge. So let's take a look at series A. So series A, we have a tweak of a P series there. We have square root of k plus 1 over k squared. And so anybody have, usually I try to get an intuition. Does that converge or diverge? So here I'm thinking, well, if it was just square root of k, let's see, where's my colors? Oh gosh, wrong button. Get over here. There we go, colors. All right, so if it was just square root of k, and I didn't have that plus 1, then that would be k to the 1/2 over k squared. And if you consolidate the k's, you're going to get 1 over k to the 1.5 or k to the 3/2 in the denominator. And so this is kind of like a p series with p equal to 3/2, which is greater than 1, which means it would be convergent. Okay, so the question is, does the inequality on that go the right direction? This would be convergent, right? And basically, I took 1 away from the inside of the square root for the other one. So this one has a bigger numerator, agreed? So if I wanted to do a direct comparison with the square root of k plus 1 over k squared versus square root of k over k squared, would you agree that the guy on the left is bigger then? Because it's got a bigger numerator, and this guy over here is equal to 1 over k to the 3/2, and so I could do a direct comparison on that. So since this is a convergent p series, p again equals 3/2, which is greater than 1, then by direct comparison, we're going to have that sum as k goes from 1 to infinity, square root of k plus 1 over k squared converges. So sometimes if the inequality doesn't look too bad, I'll just go for it if it seems obvious. If it doesn't seem obvious and the algebra of the inequality does not look like fun, then I'll do a limit comparison. So let's, questions on what I have there with the direct comparison? Okay, so I just think about, what could I do to simplify what I have? Does that simplification lead to something I recognize? All right, limit comparison is another good one for that one. So that's where we're going to take the ratio of those two. So we're going to take the square root of k plus 1 over k squared, and we're going to compare it with another series. So for example, I'm going to divide by, my guess is it converges, so you have to make a guess ahead of time. So I'm going to compare it to 1 over k squared and see what happens. Limit as k goes to infinity of this. So the sum is out of the picture. I just have the ratio of a series that's unknown with a series that's known. Cleaning that up, then I get the limit as k goes to infinity of what? The k squareds divide out, and I get the square root of k plus 1, which is infinite. Does that tell me anything? If it's infinite, I can only show divergence. And my guess is that this thing converges. So I know nothing now. So I know nothing here. Because this can only be used to show divergence, and I compared with a convergent series. What else should I try? What'd you guys try? I could try for maybe it diverges. Maybe let's make believe we don't know the direct comparison. Let's say we didn't do that. So I might say, oh, maybe it does diverge. So try 1 over k. See what happens. So then I try limit, and that's the bottom line. You're running around not really knowing what's going on. So you just got to try stuff, not be afraid to try and fail. So square root of k plus 1 over k squared divided by 1 over k. When I do the algebra on that, limit as k goes to infinity, I get k plus 1 over k squared times k over 1. So I get to get rid of 1 power of k here. So now I have the limit as k goes to infinity of the square root of k plus 1 over k. What can I do with that? Anybody have an intuition about it? It'd be nice if this was a square root in the denominator too. I could combine it all into one square root. Can I write k as the square root of something? Yeah, I could write it as the square root of k squared. So I say, hey, you can just be the square root of k squared for now. Then I can bring all this together. And this, again, as long as everything's positive, I can bring those roots together. This will be the limit as k goes to infinity of the square root of k plus 1 over k squared. And we can take the limit inside the square root because the square root behaves nice. It's a continuous function. So what happens on the inside here? What's going on in there? Polynomial denominator has a higher degree. So denominator beats the numerator. Top isn't growing as fast as the bottom, so this is going to 0. I was trying to show divergence, but I got 0, which means it doesn't work either. Okay, so dividing by 1, comparing it to 1 over k didn't work. Comparing it to 1 over k squared didn't work. So I could say, well, maybe I could aim in between k and k squared. So that'd be another option. And so we could say, well, what's right in between k and k squared? K to the 3 halves. So I could try that, see if that leads anywhere. So let's just do that for fun. Series R in exploration, limit as k goes to infinity. Now here I'm getting smart. I know that dividing by something means multiply by the reciprocal, so I'm just going to jump right to that. So you guys will find all kinds of algebraic tricks as you play with these. Times, I'm going to go for k to the 3 halves, which is 1.5 over 1. So let's see, cleaning that up, what do I get? Well, I'm going to have that square root of k plus 1. And then as far as these go, these are concerned, 3 halves minus 2 is negative 1/2, which puts a square root of k in the denominator. And basically, like before, we now have the limits, and we can bring this into 1 square root as k goes to infinity, and I can sneak inside the square roots. And what do I get? 1? No, because these have the same degree. Coefficients are 1. So this limit is 1. What does 1 tell me when I do the limit comparison? They both behave the same. If one converges, the other has to converge. We know this was a convergent p-series, so that means we have convergence. Whew, finally. So this is a case where the direct comparison was way easier than the limit comparison. And you don't know until you try some stuff. So finally, we have convergence by the limit comparison test. And our evidence is behind us there. All right, any other thoughts, questions on sequence A? Yep. I think you're always supposed to have the known series in the denominator. And I'll have to look back at the proof of that as to why, but I was thinking about that the other day. But I think it's always supposed to be unknown, over known. Otherwise, you get into some messy places. So you'll see, like our particular book, they don't actually mention the order, but they also don't go to those edge cases about 0 and infinity. So if you don't bother with saying it's got to be unknown over known, then that means you just don't have any edge cases. If you get 0 or infinity, it means you just know nothing. If you keep the order as unknown or known, then you can explore, well, what happens if I get a 0? What happens if I get an infinity? Then you can take it that direction. So the book we're using doesn't go there. It doesn't mention order, but if you look at the OpenStax book, they reference the order of them and they explore the edge cases. Okay. So if the edge cases are blowing your mind, just say, hey, I always want a real number. If it doesn't give me a non-zero number. If it doesn't give me a non-zero number, I'm gonna look for a different test. So you don't have to worry about the weirdness on the edge. And sometimes it's hard to tell by just looking at terms, because sometimes they could diverge but grow very slowly, kind of like a logarithm or square root function. So just looking at terms is not always good. Uh-oh, don't slip. All right, let's try the next one. So the next one, we have the sum as k goes from 0 to infinity of -1 to the n times n over 3 to the n. And as soon as you see something like this, it's always a good idea to list out a few terms to make sure it's strictly alternating. But pretty much anytime we have a -1 to a power like that, it's going to alternate strictly. So just double checking. The first term is going to be 0. Then I'm going to have a minus, because I'm going to have a, oops, I'm mixing up my k's and my n's. Sorry about that. These are all k's. Next one, I'm going to have a minus 1/3, and then a plus 2/9, and then a minus 3/27, and it's just going to keep going on like that. So I do have it strictly alternating. So we can use the alternating series test. Alternating series test, you have to meet just a couple of conditions. One, it has to strictly alternate. And two, the non-alternating part has to go to 0. So the limit as k increases of my non-alternating part, that's k over 3 to the k, that has to go to 0. Does this one go to 0? Yeah, exponential function crushes a linear function. If you're not sure about that, you could always apply L'Hopital's rule, because at the moment this is infinity over infinity. According to L'Hopital, the derivative of the numerator is 1. What's the derivative of the denominator? Anybody remember? Derivative of something other than e to a power? It's got something to do with 3 to the k, but there's a twist. Times the natural log of 3. If it's not e, even if it is e, that works. What's the natural log of e? 1, excellent. Whew. All right, that's 1. So here I have the numerator stuck at 1, the denominator is growing and growing, so this is definitely going to 0. So according to the alternating series test, this does converge. Now, both of these, we were able to say they converged, but we have no idea to what. Alternating series test gives me at least a leg up in that I can try and estimate the error after I approximate it. So let's look at the error in the first 100 terms here. Okay. So let's calculate S sub 100. So that would be just the sum as k goes from 0 to 100 of our -1 to the k times k over 3 to the k. The remainder theorem for alternating series says that your nth error has to be less than or equal to the next term in line. So for us, that's going to be k plus 1 over 3 to the k plus 1. And it's the non-alternating part we're looking at when we get the error. The alternating just tells us to jump up or jump down. And so for us, we want the 100th error. So the 100th error is going to have to be less than 101 over 3 to the 101, which I'm not sure if my calculator can compute that, but we'll try. Wolframalpha could. All right, so now we whip out some kind of tool. So I wonder, try it on a TI. I think this might kill the TI. I don't think the TI can do that. All right, so I am going to ask Desmos. They gave you an answer. Okay, for the error or for the sum? Which one were you trying? Okay, what does your calculator say on that? So I'm going to call it 6.5 times 10 to the, oh my gosh, so we have like 46 places of accuracy. That's pretty good. You know, we can, I don't think we need that many, but hell. Wow. So because of the geometric portion, because this is partly a geometric series, right? We just have multiple of k in the top. All right, so let's see. I'm going to see if I can come up with a number to go with that. So partial sums. Go away. Let's go up to, what did I say, 100. And we are going to try -1 raised to the I times I divided by 3 to the I. Oops, I. Okay. And here, oh, it's a small number down there. Let's, did I type that right? I guess. Oh, well, the 0 doesn't, oh, yeah, that does matter. No, it doesn't, because the first term is 0, so it's not going to do anything. So let's zoom in on this sucker y-axis. Let's go from -1 to 1, maybe. All right, so these, because that first term, which is the biggest one, it's negative, everything else is going to be negative thereafter, because this is shrinking so fast. And we're zooming in on that limit pretty quickly. So it's flatlining there. So let's zoom in on that. What are we here? That's 0.5, so that's 0.1, that's 0.2. What's up? Oh, okay, I guess I can zoom in like that for a moment. One more time, and then we'll adjust the x-axis. We want to go out to 100. Okay, so if we click on one of those guys on the end, now little does Desmos know that we have way more accuracy than 4 places, right? What do we have, 30, no, 46 places of accuracy? Probably more than that. That's an upper bound on it. And so it's, you know, about, I don't know, 1.875-ish. Okay. Oh, I doubt it's actually 3/16. Let's see, how can I get, can you tell Desmos to give you more decimal places? I don't see a place to ask for more detail. So I'm going to go to my favorite spot for lots of decimal places, Wolframalpha. So we want the sum of -1 raised to the k times k over 3 to the k, oops, as k goes from 0 to 100. Oh my, maybe it is. Would you say 3/16? Oh, okay. I bet we can prove that later. Cool. Let's put us in our things to prove soon. Our power tools, yeah. Oh, okay. Yeah, I think I know how to show that. We'll show that. Maybe on Thursday we'll be able to do that. Sweet, that was nice. Let me make a note. Let's see, this is 1.7. No, this is 1.6 stuff. So the sum as k goes from 0 to infinity of -1 to the k times k over 3 to the k seems to be 3/16. All right. Wolfram, I don't know if they have that programmed in to check with the remainder theorem. Ooh, then weird stuff happens over there. Oh, we got to count this. Let's get a copyable plain text. Ooh, what the heck is it? Oh, it's giving it to me as a fraction with 79 places. Can I copy that there? Okay. Copy that into where? An editor here, maybe? Okay, how many places do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 46. Oh my gosh. 46 decimal places. Wow, isn't it amazing when theory matches reality? Whew. Man, wow, that is wicked cool. I love math when it works. All right, so that was a review. So, oh my, we spent the whole time reviewing stuff. All right, well, let's do some non-review stuff now. Okay, new page. So sometimes series don't strictly alternate, so we got to figure out what to do when they don't strictly alternate. And it turns out it's not that bad. So consider the sum, oops, pencil, the sum as k goes from 1 to infinity of the sine of k divided by k squared. And let's see what it looks like. Let's list some terms out. So I'm interested, not the sum at the moment, I'm interested in the sequence. So I'm gonna go to that sequence grapher that I have here, and I'm gonna enter the sine of n. Whoa, that's cool. Okay, and then, oh, interesting. Let's zoom out on this a little bit before I do anything. Let's see what I want to do. I want x to come in a little closer. Let's go to 10. So my numerator is controlling, that's the sine of n, that's controlling my alternating. Does it appear to be alternating strictly? Positive, 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 negative, 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 positive, positive, positive. Ooh, it appears to be going 3 at a time. What? Oh, what's that one? That's pretty close. It can't be exactly 0, can it? Probably not. If I zoom in, or I could click on it. Oh, it's not quite 0. All right, so I have negative, negative. Oh, 4 negatives in a row that time. Darn, this is a crazy one. It does not strictly alternate, not even in patterns of 3, which would be kind of nice, but that doesn't work. So when I divide it by n squared, it's just going to be heading towards 0, but it's still bouncing up and down. So when I click on this guy, it's negative, negative, negative. We ran out of decimal places here, so we've met the limits of Desmos, unfortunately. Ooh, positive, positive, 0. Is it really 0? No, Desmos is just, we need more decimal places. So I should have had GeoGebra app ready, but that's okay. So this particular series is not strictly alternating. Okay, so it's not strictly alternating. That means I cannot apply the alternating series theorem, but you'd think, well, they're going to 0, right? We know what do we know? We know, let's see, the sum as k goes from 1 to infinity of 1 over k squared, that's convergent, right? So we're just going to do a little squeeze action on this thing. We also know that the sign of k is between 1 and -1, always, because that's its nature. Well, if that's true, can't I just divide everything by k squared and this inequality is still going to make total sense? So every single term fits this pattern. Doesn't matter what k is. K could be 1 or 2 or 3 or 4 or 5 or 6. The terms that I'm interested in lie between those guys. Well, that must mean the sums have to do the same thing. So the sum as k goes from 1 to infinity of the sine of k over k squared has to be less than or equal to the sum as k goes from 1 to infinity of 1 over k squared, and greater than or equal to the sum as k goes from 1 to infinity of -1 over k squared. And the part of the inequality that matters most to me is that side right there, because I know this guy is a convergent p-series. So what can I say about my mystery non-strictly alternating series? Convergent? Divergent? What do you think? Excellent. It is convergent. Why? Direct comparison. Yeah, I have an inequality that says, hey, this guy is always slightly less than that guy over there. Okay. And actually, because the period of the sine is 2 pi, and k is never going to be a 2 pi type number, I'm never going to hit 1 or -1. So this or equal to part ain't ever going to happen. It's always going to be strictly less than. Okay. So by direct comparison, we have convergence. Okay. Now it gets better than this. So check this out. The sign of k does wacky stuff, right? 3 positives, 3 negatives, 3 positives, 3 negatives. All of a sudden, it just throws 4 negatives at us, and it just does weird things. But what I could do is I could strip the signs of all of those, and I could just say, well, what about if I let k go from 1 to infinity, and I take the absolute value of the terms? Not the absolute value of the sum, the absolute value of the terms. Well, what do we know about the sign of k? Isn't it always less than 1 in this case? So aren't these individual terms still smaller than the 1 over k squareds? Yeah, I still, even when I throw the absolute value on the inside, which means I have no cancellation ever, right? It still converges by direct comparison. This guy is still going to be less than or equal to the sum of the 1 over k squareds as k goes from 1 to infinity. So when you strip all of the signs from the terms, that's called an absolute series because you took the absolute value of the terms. So you'll see that term floating around a lot now. Absolute, you'll see absolute series, you'll see absolute convergence. And we want to strike from our mind, you know, the things we hear from family and friends about what something absolute means. Like clean your bedroom or you're absolutely grounded. That's not what absolute means here. It doesn't mean it's a certainty, it means absolute value. So when we're using the word absolute, it's absolute value. So we're going to have an idea called absolute convergence. which a better name for it would be to sneak in here the word value. Absolute value convergence. So I'd like you to try and put that in your head. Every time you see the phrase absolute convergence, tell your mind to stick the word value in there, because that's really what it means, absolute value convergence. All it means is if you strip the signs of all those numbers, it still converges, which is pretty powerful. Because if I strip the signs, doesn't it mean it's bigger than it used to be because I got no cancellation? So what's always going to happen is that any particular series, let's call them A sub n's, those guys are always going to be less than the sum of the absolute value of the A sub n's, because we took any possible cancellations out. Okay. If this sucker right here converges, then we use the crazy terminology, which bugs me, but it's what it's in every book, so I'm stuck with it. Then the sum of the A sub n's converges absolutely. So that's the phrase you'll see all over and over again. People, you watch videos about it. I don't care where you watch it, Khan Academy or my friend James at Math is Power for You. They all talk about, hey, this series converges absolutely. Like stamp your foot, absolutely. What it should really say is it converges in absolute value. That's what we really mean. Ooh, whoa. Got too excited there. Converges in absolute value, which is really powerful because if we strip all the signs and it still converges, that's awesome. We have convergence everywhere. Okay. There's another idea called conditional convergence. What that means is this guy converges, but that guy doesn't. We strip the signs and we get in trouble. Okay. That's called conditional convergence. On the condition we don't strip the signs, it still converges. Okay. So we'll talk more about conditional and absolute. The cool thing is if the absolute value of the series converges, means strip all the signs, then the regular series has got to converge because it has tons of cancellation going on, which is nice. So this is like a slightly more general version of the alternating series theorem, although we can't say anything about the remainders, which sucks, because we don't have that strict oscillation in sign. That allows us to say something about the remainders. So here all we can say is, yep, we got convergence, or sometimes we have convergence, or we never have convergence. So now we kind of have three categories. We have absolutely converges, which isn't really an exclamation, it's just, hey, it converges in absolute value. Strip the signs and it still converges. And I don't know, that just, it bugged me and I never quite got over it. I went to therapy about it and I'm almost better. Someday I'll get all the math editors to rewrite what absolute convergence means and not use that phrase, maybe. Yeah, I'm working on that. I need to go time travel for that one and find out whoever coined the term imaginary and say, no, bad idea. You're ruining our lives. All right. So we've done